Hello everyone, I'm Nivedita Shetty, a formulation scientist at Genentech. Prior to joining Genentech, I pursued my PhD at Purdue University, and my research interests mainly focused on particle engineering to enable dry powder inhaler formulations. In my today's talk, I would like to highlight some of the key findings from my PhD research that focused on improving physical and aerosol stability of spray dried high dose dry powder inhaler formulations. As you all are already aware, inhaled therapy is a combination product. It is an interplay of three major factors: the patient adherence, the type of device selected, and the formulation aspects. All these three factors play an important role in determining the optimal aerosol delivery. For the sake of this presentation, I would like to focus on the formulation aspects of mainly the dry powder inhaler formulations. Spray drying has been used as a viable technique to produce these dry powders for inhalation. It is a very rapid technique which tends to produce amorphous powders at the end of the process. Upon storage, these powders have a tendency to convert to the more stable crystalline form. In my research, we try to understand the impact of such conversion on the aerosol performance. And for this purpose, we use ciprofloxacin hydrochloride as a model drug. To understand the effect of recrystallization on aerosol performance, we spray dried ciprofloxacin and stored it at moderate humidity conditions of 55% RH for up to 3 weeks. And as you can see, the blue curve shows a completely amorphous formulation right after spray drying, which had turned into a crystalline formulation after 3 weeks at moderate humidities. We then correlated this finding to the fine particle fraction. And as you can see, there was a significant increase in the fine particle fraction when the formulation was stored for up to 3 days at 55% relative humidity, and it then further plateaued at up to 3 weeks. But we did see a proportional increase in aerosol performance when the samples recrystallized at moderate humidity. So right after spray drying, the particles had a smooth spherical surface. However, upon storage at 55% humidity for 3 weeks, the particle morphology had changed and the surface was rougher, and because of this there was reduced particle-particle interaction, leading to an increase in the fine particle fraction. This is a concern in terms of the product quality upon storage, as the aerosol performance seems to change with change in solid state and particle morphology. To prevent the crystallization of spray-dried ciprofloxacin, we decided to add another antibiotic, colistin, which has a much higher molecular weight, and it would act more like a polymer, thereby self-assembling and enriching on the surface of the particles during co-spray drying. Upon co-spray drying, colistin with ciprofloxacin in the mass ratio 1:1, we observed that colistin completely inhibited the crystallization of ciprofloxacin even when stored at 55% relative humidity for up to 2 months. We then investigated the particle morphology, and as you can see, spray drying ciprofloxacin alone drastically changed the morphology, making them rougher. However, adding colistin to the formulation did not show any change in the surface morphology of these particles. We further investigated the fine particle fraction for these co-spray dried formulation upon storage at 55% relative humidity for up to 60 days. And as you can see, adding colistin to the formulation significantly increased the fine particle fraction to about 70%, and there was no change in the fine particle fraction for up to 60 days. We further examined the surface of these co-spray dried particles by using a quantitative surface analysis technique called the X-ray photoelectron spectroscopy. And as you can see here, theoretically we had 50% colistin in the formulation, but the measured surface composition was about 74. So we did see an enrichment of colistin on the surface. In summary, adding colistin helped improve the physical and aerosol stability by enriching on the particle surface and preventing change in the fine particle fraction during storage. I have provided a very high level summary, but more detailed findings have been published in the Journal of Molecular Pharmaceutics. I would like to thank my advisor, Dr. Tony Shu, for all his support, all of my lab members, committee members, and all the funding that I received to enable this research. Lastly, thank you all for your kind attention, and I will be happy to take questions if any.
Well, thank you very much for that very interesting talk. There are a few questions coming in from the audience. Before we come to them, I just had one. I'm not sure if you commented on the total dose that you were trying to deliver from your device in this. You spoke about your fine particle fraction. I don't remember you saying the target dose.
I'm sorry, could you repeat that bit, the last bit I missed on that? Did you say the total dose or the emitted dose?
The dose you were targeting there.
Yes, so I think in my presentation, I was mainly focusing on the fine particle fraction, which is the particles with the aerodynamic diameter less than 5 micron. And just in the interest of time, I did not show the emitted dose.
Yeah.
But with all these formulations, we had an emitted dose of above 85%.
Okay, but
there were no differences in that.
Yeah, but I was just thinking in terms of the, was it 50 micrograms or 5 milligrams, say, you were trying to deliver? What just the order of magnitude would be interesting.
Oh, so when we did the study with the NGI, we loaded about 20 mgs of the powder in the capsule.
Okay.
Yes.
Thank you.
And can I ask, your fine particle fraction went up when you included colistin. Do you have a mechanistic explanation for
that? The fine particle fraction increased when I added colistin.
Yeah, as well as stabilizing the formulation, it increased the fine particle fraction. Did you have an explanation for why the fine particle fraction increased?
Yes, actually, that's a very interesting question. And there has also been some studies that has been done with just colistin and some other molecules. So I think colistin, just like leucine, has an aerosol enhancing capability because it has it works by this mechanism, especially during spray drying, that it enriches on the surface of the particle, and it's being an amphiphilic molecule, it rearranges itself in such a way during spray drying by enriching on the surface and improving aerosol performance. So I think that is kind of well studied, and that's what we see in the results here when it's co-spray dried with ciprofloxacin.
Yeah, and I guess in an antibiotic formulation, adding a second antibiotic may have a therapeutic benefit, but if that weren't the case, are there other molecules that you might use to achieve the same stabilizing and aerosolizing, enhancing effect that colistin seems to have had?
Yes, so actually we did not try another antibiotic or a drug, but we did try different kind of excipients like some sugars and leucine as an amino acid, and also these results have been published in International Journal of Pharmaceutics. And leucine, just like colistin, also has the same protection and increasing the aerosol performance effect. We did see that with these with leucine in particular, not really with the sugars. But yes, we haven't tried any other molecule, but I think it also would be case specific. Like colistin for us worked because it is a large molecule and behaves like a polymer, thereby enriching on the surface. So we definitely will have to look into molecule properties, and it would differ.
Okay, thank you. In the interest of time, I think you're joining the New Researcher Network discussion forum. So that'll be a great opportunity for anyone whose questions haven't been asked to discuss them with you in person.